So let's go to Q&A session. And I know you covered a lot of ground. Actually, there was a lot of discussion in there. I think that when you mentioned the black surface, I think you were talking about Vanta Black. I put a link up to that in chat. But then you covered so many other things. There was a lot of discussion there. So who would like to go first for Q&A?
Oh, good. I can go have a smoke.
do you want to take a moment?
No, I'm fine.
Oh, okay.
I'm fine.
Okay. Yeah. I mean, again, there was a lot. They were talking about Planck black body radiation. I was trying to follow the chat to see where the questions might be. And then they were having a discussion about classical versus quantum bodies and stuff like that. They chatted briefly about cells. So there was a lot going on that came out of what you were talking about. So let me see. So again, guys, post questions in chat or raise your hand. There's Mr. Riken. Sir?
Okay, so on slide 26, could you explain, do you have the data for that and explain your experimental setup to get the data that supports the graphs that you've made?
Slide 26, let me look at it.
Yeah, I'm sorry. And if you need to put that back up on screen share, go for it.
It's actually published as a paper. Oh yeah, put it in the book. It's also in the books. Let me look up. Oh.
Yeah, if you could just explain how you did the setup and how you created that data, that would be.
Yeah,
that would
it's basically
explain a few things. I just felt that you kind of glossed over that.
Yeah, because that's a lot of things I've glossed over because there's a ton of work behind each of these things. And then I may write a paper and think that this is correct, and then a few years later I come back and say, no, there's a better version. So if you follow through the papers, you'll find that there have been changes I've made based on what it is. Basically, you have a nanowire and a photon passing through it, and the surrounding metal is silicon oxide. So you model the probabilistic wave function from here all the way out. And the electric field will change based on the, permittivity. And then—
So the nanowire is silicon dioxide? Silicon oxide?
No, the surrounding medium is silicon oxide. The nanowire, I believe, is made of, I forget what it is. It's been around a decade since I've worked on that. So all you do is you model the probabilistic wave function around that nanowire, and then you get those graphs.
Okay, so it wasn't actually an experiment with actual—
No, it's not an experiment. It's a one-for-one comparison with Urlan's, I believe his name is Urlan's, modeling of experimental electric field in nanowires. So it was basically one model compared to a different model.
So not experimental data.
No, it's not experimental data. Most of my data is not, most of my results are model results, but they are based on experimental data.
Okay,
so I don't how
experimental data for that.
What
was the source for your experimental data?
I have to look it up. Just give me a second. I can get you the— I can tell you what to Google.
Yeah, that's probably good. And if we get too in depth, we may have to.
Sorry. Okay.
Oh, no worries. But yeah, if we get too in depth, I just don't want to stall everybody out. So that could be something to follow up on afterwards.
So he can put that in chat, and then I can check up on it later. If I got questions, I can send some mail to him.
Okay. Okay. Awesome. Well, thank you, Will. Thank you. So let me see. While he's looking that up, and we actually had a couple of questions in chat, but I'll wait just a sec because Benjamin is looking. He's looking up those values.
I have to find the file first.
Oh yeah, no worries, sir. No worries at all.
Was it 14?
You can email that to me or send it to the group later. That's fine.
Okay.
Thank you very much for answering my question.
Yeah.
Okay, well, and thank you as well, Will. Okay, well, let me move along then. So HT Alvarez, who may or may not have audio, I think he's had problems with that in the past, had asked, and let me see, I can do ask to unmute. I can give that a try, but that may not work. What he had asked was if there was any data on the Chinese test in orbit.
No, that I don't know.
Okay. Okay.
I know Shoya did talk about the Chinese test. I did not. I found an article 1 or 2 years ago about it, but I didn't keep the reference. It was not their paper. It was an article about their paper.
Okay.
Yeah. So if they Google the Chinese test for EM drive, you should be able to find it.
Then let me jump down a bit. Michael Richardson had asked, how do you gain thrust with no mass? And I think, well, this definitely gets into what you were talking about. It gets into photon rockets and stuff as well, right? But
yeah. So to answer the question, photons may not have mass, but they have momentum, which is puzzling, but it's correct. It's experimentally verified. That's why you have the photoelectric effect, is because not only are photons particles quantas, but they also have momentum. And the energy of that effect, the excess energy of, because you have to kick an electron, you need a certain amount of energy in the photon. And the excess energy is seen as kinetic energy of the electron that has left the orbital. So it's a surprising behavior. It's a surprising observation of nature, but you do not need mass to have momentum, and photons are proof of this. I suspect it's due to the wavy function, that space wave that carries momentum, and that's about it.
Thank you. Let me see. We had another question by it's a rather large name. He was saying he makes self-organized nanowires and nanotubes for monatomic compounds. He was wondering what you would recommend to use those harvested materials for, like a transistor structure, perhaps, or.
Can you say that question again?
Yeah, I'm sorry, and it's in chat. It's the last one down there. And I can ask him. Let me see if I can.
I'm looking.
It's Burn Mind's Eye. Actually, it's a much longer name than that. I'll ask him to unmute. See if he can ask it himself.
Oh yeah, nanowires and.
Yeah, so it looks like he's making structures himself, and then, oh, okay, he's chatting. He said he needs a minute. But yeah,
this is a very easy question to answer. I'm not an engineer. I'm a theoretical engineer, so I couldn't help you with that answer. I have an engineering background, but I haven't used it. I've used the engineering thinking process to help me a lot. I think it's very important to have an engineering background when you're looking at these sort of things. But sorry, that's not a question I can answer.
Oh, no worries at all. I feel the same way. You don't use it, you lose it, right? Even if you use the hands-on stuff has left me long ago. So. Let me see. So does anyone else have questions in chat? We have more time. We have Jeremy Reese up there with the click the like button on his desk. That's kind of interesting. Michael had asked about momentum with no resistance. And so I think he was that. Michael, why don't let me see if I can unmute you. Let me see if I can get him unmuted and then he can, okay. Michael, are you with us?
Yeah, I'm fine. I can hear you. Can you hear me?
Yeah, perfect. Go ahead, sir.
Okay, so I'm confused. Momentum with no mass. Momentum with no resistance. I do not see how thrust can be accomplished.
Okay.
You need resistance. You're going to need resistance, and you have to have momentum with mass in order to have a thrust. There's a contradiction. There's a contradiction in physics, and I think that you're risking letting people believe in something that's not real.
Yeah, well, and Michael, what Benjamin is talking about, what he's talking about is very well documented. So I understand. Yeah, it is confusing, but it is very well documented. Remy has posted a little bit in chat as well on this.
Okay, but it's still very confusing, and I can't wait to see an EM drive with 1 gram of thrust.
I'm not surprised because the thinking has to be absolutely clear when you're looking at these sort of things. Scheuer and his colleagues before him had proposed a certain way that things could work. And a lot of people, I think about 4 people, have produced results and said it can work. And others have produced results and said it doesn't work. So the whole thing is a confusing mess. What I've done is, because I've done a lot of work on the probabilistic wave function, I've applied it to Scheuer's M drive to figure out how can we make it work better in a repeatable manner to get better results, so that we can prove once and for all, yes, it works, no, it doesn't. Clear that confusion, clear the doubt.
Okay, so when is that going to happen?
It depends. When I contacted Scheuer a few weeks ago. He said he's no longer building these things. He's acting as a consultant now to other organizations. So it's basically whoever builds those test models to run it. And they now have the guidelines. What I've done is basically put forward guidelines for other people to go out and build and prove or disprove, taking into account Tajma and his team's critique of how experiments should and should not be done. So
there has to be an end game. There has to be an end point.
Yes.
There has to be a, and we have to get to a point where we look at the future with reality rather than confusing data that sends us into confused worlds that don't exist.
Yes, science is like that. If you read all the papers, there are different opinions about what is happening and what is not happening in the sciences, especially in physics. And it's true also in medicine, it's true in finance. There are opposing, conflicting views, but eventually the more correct views will get filtered through, and we'll have a better idea of what really works and what really doesn't work. Yeah. If we don't allow all these different opinions, then we'll never know for sure.
And it sounds like, if I could jump in, it sounds like kind of one of the things that Michael is really suggesting is is that we need to be able to draw a line in the sand at some point on some of these ideas, right? And
Agreed.
Absolutely, yes,
I
totally.
I completely agree with you, because some of the stuff I've been addressing has taken years to figure out, hey, is this what this guy is saying is right, or is this what this guy is saying is right? I have to go back and hunt and figure out, hey, what were the implicit axioms? When people write down articles, when they write like the Chiao and NIMS experiments, it sounds right. But when you have an alternative hypothesis, you see the experiment differently, and you see it's not quantum tunneling.
Yeah, okay.
So that takes time to sift through and figure out what is right and what is wrong. If you read the science journals,
it shows a fundamental flaw in our academic ability to agree of what is reality and what is not. And if the academics are blind, then who is the ones that see?
I don't know. I don't know.
These are all, yes, Michael, these are, yeah, you're touching on some issues that are much larger than our conference. But yeah, I think they're very real points. It's, you know, and it's interesting to mention that in the chat during this, you know, there were several other issues that were mentioned as well, right? Where it just, perhaps we're reaching the end of some of these models. But again, that's, Benjamin, that's one of the reasons that I appreciate you presenting this so much for us, because it helps to be able to look at these ideas from different perspectives and, you know, see what reinforces and see what the disagreements are, and potentially find areas for leverage.
Yeah.
So, well, Michael, let me move on to some more questions. Let me see, who has another question for Benjamin?
I have a question. My question.
Go ahead, Lulu.
All right. My question is, do you think the disagreements between the results of in the physics is because each one measures in a different standard? You know, like we don't, you know, some sides of the world have different metric measurement systems than the ones that we have here. And, you know, when you're converting these to meat, like, wouldn't the disagreement be in the conversion ratios?
No. That's a viewpoint that a lot of people have. And it's an interesting one. Basically, from the point of view, it raises a lot of questions in my head about that train of thought. But actually, most of the disagreements are coming from not the measure, but how we measure. So when we use a piece of equipment to measure something, we are not just using that equipment, we are using a theory that is the basis of that equipment. So it's actually two steps back. When we measure, we are looking at, okay, this theory says this, and therefore we use this set of equipments, and therefore we observe this. This theory says something slightly different, so we
The equipment from the theory, because you couldn't have an equipment that, you know, doesn't support the theory.
yes.
So when the equipment is a machine that you code with these theories and these formulas, and you know, so it just depends on the, you know, how the machine is able to read these theories on what was the original, you know, input.
Well, yeah, Lulu, if I could make a suggestion, what you mentioned about different systems, I think I just read a large article the other day about disagreements between you know, relativity theory versus quantum mechanics, right? So I think it's a good point. I mean, it's, you know, physics was developed using a lot of different standards, and I don't think they always match up.
I mean, this is what I'm saying when, you know, there's disagreements. It's just if they can go back and unify the, you know, two ways of measurement, how the perspective from, you know, whatever like the angle of how they're, you know, doing their calculation. And I'm pretty sure it will match up at the end. It's just, you know, we're comparing two sets of probably two different, you know, sets of things, you know, on how it's measured. So things might come out a little bit different.
Yeah.
I mean, plus you have like core chips, like the for anything, and it just depends on the substance that it's made out of, you know, because if you measure the oscillation of anything, you know, compared it to another atom, it might not be the same. That's why we have the spectrum of like the higher frequencies and the lower frequencies. And so,
absolutely. Thank you. Well, Lulu, let me go now. Let me see. I had another one from guest 314. Let me see. Oh, I think we may have just lost her there for a sec. He had asked, let me see. Okay, there's Lucy's iPad. Sorry about that, guys. Okay, I think we just lost her completely. Benjamin, could you explain, let me see, how wavelength is affected by amplitude? General RF does not agree.
Okay.
Oh, that was Ivich from YouTube. I'm sorry, that was a YouTube question.
Okay, basically there is a fixed relationship between, energy is basically the size of the wavelength, and it shows up as frequency. That's the energy of the photon. But there is another structure in there, which is the electromagnetic transverse wave. And it has its electric field intensity and magnetic field intensity. When you, with a long wavelength, you have a higher amplitude of the electric field intensity and the magnetic field intensity. With a short wavelength, you have a smaller electric field, maximum electric field amplitude and magnetic field amplitude. So what is effectively happening is that the photon is a store of photon energy plus electric and magnetic field energy. So how much photon energy you see is taken out of the electric and magnetic field energy into the photon energy. So the lower the energy, the more electric and magnetic field energy there is. The higher the photon energy, the less is it. So it's a hyperbolic function. Okay, that is according to the theory that I've developed. The theoretical structure that I've developed. Quantum theory says something else altogether. Okay, so when you look at a piece of paper which says this is what it is, you have to ask the question, is this empirical data or is this a theoretical model?
Well, thank you. And I think that's really important to point out too, is that you're discussing your model today and how that, you know, like could potentially replace QM or could potentially offer answers that QM can address. And so yeah, when we're talking about it, we always want to make sure like what model we're working within. Yeah. Let me see. I think okay. And let me see. So yeah, someone else is connecting their mic, and then Eric Hermanson. Eric, do you want to go, sir? Let me ask him to unmute.
Hi, Tim.
Hey, Eric.
Oh, no, I just made this comment after reading Scheuer's paper. His EM drive, it won't work unless it's given an initial momentum kick. So something on the outside of the drive has to push the drive to get it moving. And then apparently, I don't know if I agree with this, I haven't studied it enough, but during the acceleration phase of this initial kick, this starts off a process where the reference frame of the two different reference frames are created, one where the photons exist and one where the craft exists. And there's a differential, there's some kind of differential where there's an amplification process, and the photons that are bouncing back and forth, they become more and more blue shifted every time they bounce back and forth. They somehow gain energy through I can't explain it because I don't understand how it works. I'm trying to remember what the paper said. But Ben Solomon was saying something similar, where he was saying that the gravitational field inside of the craft, or inside the EM drive, was causing the photons to become blue shifted. But Sawyer's saying something different, where it's this initial acceleration. It's this, literally a force from the outside of the drive needs to push the drive to get it moving. And then during that very tiny amount of time where the thing is accelerating until it finally reaches its cruising speed, that little offset there somehow starts an amplification process that continues to grow up to a limit that's dependent upon the materials and the geometry of the drive, and the photons that are pumped in are able to become blue shifted every time they go back and forth a little bit more. And then the cavity gets hotter and hotter, and then it starts bleeding off heat. And so there's a maximum theoretical threshold where this thing can't go any faster. Its velocity can't be raised any higher.
Okay,
Great.
That's my understanding.
Yeah.
Anyway, that's all I wanted to say.
but thank you. Eric.
I think those are very sharp points to think about, Eric. There are a couple of differences. First, in my description, the gravitational field is basically an analogy to show that nature is doing this kind of energy gain, and therefore nature allows such a thing. So why not man come up with a technology that does this kind of energy gain? That was my reasoning behind that, because everything that we try to do, we have to find an example. At least that's my current belief. We have to find an example that shows that nature does it. And that's why I use the gravity as an example of an enclosed, a section of area of space-time where you look at one side, it's a red photon, and the other side, it's a blue photon. So basically what I'm saying is, if you're looking at energy increase of photons in empty space, nature is already doing it. And so can we have a technology that does the same thing? And it looks like the M drive, choice M drive, is a technology that could be doing the same thing. Okay. And what I've done in choice M drive is to show, using the probabilistic wave function and the properties of the probabilistic wave function, not the Schrodinger wave function, because the Schrodinger wave function will not give you those results, is that you can increase the frequency, you can decrease the wavelength or increase the frequency of the photon by altering the electric field amplitude, which is, and then when it bounces, let's say it bounces on the front side, it does not, because it's controlled by the electric field, it does not increase energy with each bounce. It goes back to its original energy state, because the two radius control the energy of the photon at that moment, at that location in the wave in the waveguide. So you have original energy, increased energy. If it bounces back, you go back to original energy, and then you bounce and you come back to increased energy. So you go back and forth. The energy state of the photon is fixed and by the two radii. And I believe that Scheuer said something about increasing velocities. I do not believe that explanation is correct. And that's the other thing I stay away, because there's this concept called waveguides group velocity. Group velocity, if you look at it, if you look at the individual photons are still individual photons. They come together collectively and have a collective behavior, but that doesn't mean that they are now a collective animal. And you see this a lot in statistics. Let's say some event has a base Weibull distribution. Let's say failures or reliability. They obey a Weibull distribution, which is basically a distribution that is skewed to the right. But if you take the average, the averages behave as a normal distribution, and normal distributions are easy to solve. So you find in physics, a lot of things are looked as a group. And so you have a group velocity because the mathematics is easier to solve. But if you don't look at it that way, it's very difficult to solve. And that's why when physics puts things together as a group, I tend to, okay, it's there, okay. Let's look at the individuals. What are the individuals doing? And therefore, my personal opinion is I tend not to believe, to take group velocities so seriously, because unlike some theoretical physicists, because I think that's a collective behavior and not the individual behavior. If you want to model something, we have to look at the individual behaviors. I hope I answered your question. And your questions really have to clarify some differences between what Scheuer was explaining and what I was explaining.
I think you did. Thank you. You know what? Let me go to Jeremy Reese. He'd asked about 4-wave mixing, but let me see if he's back yet. Jeremy, do you have any questions from YouTube as well while we're here?
I didn't see any. Eric mentioned a scheme for using a pump wave to inside of and I thought of 4-wave mixing. That was that comment. Anyone have any questions live? Anyone have any questions live? Please post them. I didn't see any. So, but thank you. That was great.
I like your background also, Jeremy. Hit the like button. So. Okay. So yeah, we're continuing to roll here. I think Bernie had a question also. Bernie, would you like to go, sir? He was asking about Robert James Moon.
Can you hear me?
Yes.
Okay, just give me 1 sec here. I'm trying to upload a couple of reference pictures to the chat to use to ask Benjamin.
And Bernie, I love your background. I love that. That's wonderful.
Thank you.
That's all blacklight art, right?
Yes, sir.
Yeah, so let me see. It looks like we had a question here from Esoteric Gold and a question from Simon Claret on, he said squeeze states of light. Anything about squeeze states of light? Since photons are neutral in charge, they contribute greatly to these advanced technologies. The question is, how do we capture them?
Capture photons. It's going on all the time.
Neutrons.
Neutrons. Neutrons, it's standard nuclear physics. It's not my area, but it's standard nuclear physics.
They use like the graphite, like the water.
Yes,
water
like
shield.
the graphite. It interacts with the neutrons, interact with the nucleus, and they bump up or split up the atomic structure during the capture process. But that's standard nuclear physics, and it's not my area. I would love to have been able to answer that question, but it's not my area.
I had another question. I don't get the contents. It says, please explain how wavelength is affected by amplitude. General RF does not agree.
I just explained that a few minutes ago.
Yeah.
Oh, yeah, we went through that one, Jeremy. I think Jeremy was out. I should apologize for that.
I stepped out for a minute, so, but I'm back now. Yeah, I can't find the other question. Sorry. They said there was another question
Oh,
here, but
no
I can't
worries.
find it. I don't know.
Oh, there's a question here which says, can virtual particles be generated by microwaves? That's an excellent question, because this is where I disagree with current theory. There's this critic that really got me. There's this critic of M drive. And he's saying, we have used virtual particles to prove that this does not exist. M drive cannot work. Wait a minute. Let's sit back and think. Why did they call it virtual particles? Because they don't exist. It's a mathematical structure to solve a mathematical problem. It's not a mathematical solution to solve a real world problem. So how can you use a fictional particle to disprove an experiment that is still being matured? Fiction, right? Virtual particles don't exist. The scientific community will tell you, yes, it exists, but nobody can prove that it exists because it doesn't. It's a mathematical conjecture. It's a mathematical structure to solve a problem in quantum theory.
So that kind of reminds me, when you were talking about group velocity, right,
Yeah.
versus individual. It's kind of the same thing then.
Yeah, and that's why a lot of times we see a lot of these kinds of issues in physics, because we are not careful enough to say, hey, wait, stop, let's sit back and think, is this real? I know my professor from 2 decades ago said this was real, so I'll assume it's real, but maybe not. We don't do that sort of things. We need to do more of that sort of things. Look at what we're doing. Is it real? Or was it a mathematical construct that somebody invented to answer some questions? We want to find out what is going on in nature, not what model works.
Absolutely. So Bernie had posted, let me see, Bernie, are you ready to go again now, sir? He posted a couple photos in.
Yeah, do you want to bring the photos up?
Yes, I can do, if you'd like, I can do a screen share. Let me see if I can make that work. Okay, sorry about that. And let me go into chat. Okay, so there's the hydrogen wave function and orbitals. And okay, and cymatics. Do these all look good, Bernie? Can you guys see me okay?
Yeah, absolutely.
So what was your question, sir? What?
So when you look at these references, it highly supports Mr. Solomon's area on standing wave energy creating the dimensions of matter. And it's uncanny how the hydrogen wave functions are identical to planes of quantum number dimensions, as well as geometric sacred geometry patterns, and that this is essentially a good area to lead into Jason Verbelli's presentation and his dimensional geometric theories, and but it's noticing all the patterns and shapes of how the energies move and transform from state to state of different like motions, heat, electrical, magnetical interactions and reactions. And yeah, sorry, that just not really a question, more just a background to kind of connect things.
Okay.
That-
Oh, I'm sorry.
Yeah, no, it's okay to bring it up because this goes back to an earlier comment. When we look at these patterns, these look like model results rather than actual empirical data. So you have to be careful when you look at something. You have to ask yourself, is this a model result or is this empirical data? For example, I did a really silly thing about 10 years ago when I looked at Woodland's paper. There was a picture of this bright center of the nanowire, and I sent him an email and asked him, which he never replied. I asked him, wow, is that actually a photograph of a photon and a nanowire? I fell for it, but it isn't because you cannot see a photon.
I believe that the hydrogen wave function is all actual images caught from the Sapphire project's plasma, and the center one of the hydrogen, I think it comes from an electron microscope or something. And then the bottom one is all pictures of cymatic frequencies captured resonating in water at different Hertz frequencies. So these are actual scientific results and images of real structure.
Okay, that may be the case. I don't know what to think. For me, they look too, for something that's under motion and that's experiencing Brownian motion, and also there's the other kind of motion that's called the Levi walk, which other things observe. When I look, personally, I am a little bit skeptical because of the stuff I've read in scientific journals. This may be genuinely correct photographs, or they may be models. And given that there is so much Brownian motion, I don't know what to think, really. I know a lot of people really want to find out what's going on, and they believe that this is really what's going on. But I have read so much rubbish in scientific journals that there are times when I just don't know what to believe, what I read.
Absolutely. Well, thank you. So let me stop the screen share then. I'll stop the share on that. And then, so we've got about 5 minutes left. Let me see. So I guess I should ask if anyone else has any other questions. Again, Benjamin, I can't thank you enough for joining us and presenting today. And it's exciting to see different models. I mean, that's one of the things that's always excited me, right? Is just casting a different light on the same experimental evidence, looking at things from different perspectives. I think it helps, that diversity of ideas that helps us break out of,
no, a lot of kids are graduating from physics school saying there's nothing left to discover. I mean, what? How can you graduate kids out of school saying that there's nothing left to discover?
Well, and that's happened before, right? They wanted to shut down the patent office 100-something years ago. There's nothing left to invent. And, and actually in an email chain earlier, one of the things I'd mentioned to Remy was I think that the mainstream physics community itself will probably overthrow physics because of what you've just said. Everyone wants to make their mark. Everyone wants to make a difference. And I don't think you can graduate students and then say, oh, by the way, it's all done. There's nothing you can do. You know? So wonderful.
Hey, I have a quick question.
Oh, go for it, sir.
I just wanted to know what your guest thought about the legitimacy of renormalization in quantum electrodynamics.
Don't know anything. I stayed clear of it. Once I realized that the so many bugs or so many things I disagree with quantum theory, I decided no more. I'm not going to sit down and spend my life trying to build an expertise in a field that I do not believe is correct.
Yeah, makes sense to me.
Yeah.
Yeah, Feynman actually, you know, he won the Nobel Prize, and then afterwards he questioned like why he won it and said you know, it was magical, you know, he said he questioned the mathematical legitimacy of the whole enterprise.
Yeah, he's a great guy.
Yeah.
For somebody
Well,
to stand back and say that sort of things is a really great guy.
Well, thank you.
Yeah, and thank you as well. So we have, I think we have just about 2 minutes left. If anyone else has any other questions for Benjamin. Okay, so I think we're just about all set, guys. Well, so let me do this then. Let me mute everybody back out. Okay, and I'm gonna put it back on gallery view. And again, everyone, please give Benjamin Solomon an enormous hand. Thank you so much, sir, for your time and for presenting that. I mean, that was very in-depth and a long Q&A session as well. So, okay.